Good morning and welcome everyone to the headphone measurement basics. My name's Steve Temme and I'm going to talk about what to measure and what does it mean. I'd like Alan, if you could just take a moment and introduce the S&V team.
首先感谢大家参加这个 SV Sample 跟美国 Listen 公司联合举办的这个关于耳机测试的这个网络研讨会。那今天的研讨会呢，将由Listen 公司的总裁 Steve Temme 先生主讲。那么研讨会的时间的话，持续大概1个小时。为了保证这个网络研讨会的顺利进行，所有人的这个电脑将会被设置成静音。如果各位有什么问题的话，可以在聊天室里面以文字的形式提问，中英文都可以。那我们 SV 的团队的话将会在那里作答。那么请确保这个问题的话就发给这个，它下面有个选项叫组织者 organizer only。那么在研讨会结束之后呢，我们会向这个今天的与会者发送这个问卷调查。那么与会者将会在填写这个问卷调查之后呢，就获得本次研讨会的这个演讲的文档，就是电子档。所以在此感谢大家。
Thank you, Alan. Okay, introduction. So I'm going to talk about obviously how headphones work. I'm not going to go into a lot of detail, but just the basics. I'm going to talk about how to measure headphones and in particular the different types of headphones and the different types of acoustic ear simulators, both very important when making measurements. I'm also going to talk about different acoustic test environments, in particular R&D versus production. Some of you might be in one or the other or both. And then I'm going to talk about some of the critical measurements that you need to make when measuring headphones. For example, what I call the corrected frequency response. I will go into more detail about that. Left-right ear tracking, distortion, max SPL, etc. So the anatomy of a dynamic headphone driver is really very similar to a loudspeaker, but with essentially fewer or smaller components. So the thing to keep in mind is that typically headphones have to be very flat because they're being held close to the ear and there's not a lot of space. So we still have a magnetic circuit, and we're going to have probably much smaller, flatter magnets. Obviously, if it's a dynamic headphone, there's going to be a voice coil. Again, it's not going to be as long. It's going to be much shorter. And of course, if we apply AC voltage, this is how we get the voice coil to move up and down. Now, the diaphragm is actually quite different than what you'll find in a typical conventional dynamic loudspeaker. Again, it has to be rather flat because of space limitations. And the diaphragm will be essential to how much air we can move, which also determines, depending on the design, how low in frequency it can go. This is where headphone drivers are quite different. They typically have no spider. There is just no space. And as a result, their way the voice coil is centered is a little trickier. There is no surround. Instead, there is basically usually kind of a corrugation of the diaphragm to act as a surround and to help stabilize vibrations. Again, this is to keep it simple and keep it compact. And there generally is no dust cap to keep small particles from falling in the magnetic gap. The diaphragm is typically part of the dust cap, if you want to put it that way. But one of the things that happens, unlike with conventional speakers, with dust caps, you can have soft domes. Typically, the diaphragm in a headphone speaker is quite rigid. And if you're not careful, if you get a wrinkle or a little crease in the diaphragm, you can create a buckling motion and kind of get a sharp snap. So that's one of the defects that you got to be a little careful of when you're creating the earphone driver diaphragm. I've been able to pick that up on a production line with loose particle detection. So principle of operation is really very straightforward. It's based on, I don't know how many people studied this in school, but Fleming's left-hand rule, which is for motors. And there's also a right-hand rule, which is for things in the opposite direction, like a microphone. And basically, we got the magnetic field in one direction, current flowing through the voice coil in another direction, and this creates a alternating force, which moves the air or the cone in and out to create sound pressure. I'm not going to show it to you, but I did put a link to a YouTube video if you want to see a dynamic video of the voice coil moving up and down in a loudspeaker. So one thing I'd like to remind people is there's a big difference between a passive transducer and an active speaker. So if we're just studying the raw transducer, it literally has no input or output without some signal going into it. So as a result, earphones do not make sound or noise by themselves. We have to put a signal in to get some sound out of them. And that is not necessarily the case for an active device where there's an amplifier and you can have, you know, electronic noise coming out of it or even some sort of interference going on. So I'm just going to be focusing today on earphone transducers, passive transducers. All right, there are many different types of headphones. Probably the most common, or at least the oldest design, is circumaural headphones, or otherwise called over-the-ear. If they completely go over your ear and cover your pinna and get a good seal, you should get a good bass response and also isolate some of the background noise. Oops, what happened there? Sorry. There's supraaural headphones, which sit on the concha. So those are pretty common, but I would say they're becoming a little less common. And the tricky thing with supraaural headphones is position's quite sensitive. If you want to get good bass, you typically have to move it around and get good seal. And even the high frequencies, to a certain degree, have to align pretty well with the ear canal. Of course, oh, geez, sorry, something's going a little haywire on my PowerPoint. Okay, let's hope I can control it. The next is earphones and earbuds, and typically you think of AirPods as a good example. They actually are also known as intraconcha, so they're sitting in front of the ear canal, but they're not sealing the ear canal. Again, very position sensitive and very, the low frequency will depend heavily on how well it seals with the ear canal. And then there's in-ear headphones, which basically insert into the ear canal and typically give you decent background isolation because they're sealing the ear canal. And they're also smaller, and typically you can get very good bass out of them. Now, there's this growing amount of sports-related headphones, and one of the popular ones I'm seeing now is bone-conducting headphones, and they have the advantage that, first of all, if you're running, you can easily hear what's going on around you, which is probably important. If you're crossing a road, you don't want to get hit. It also is kind of nice because generally when you're exercising, you're sweating, and you don't want your expensive AirPods falling out of your ears. So they will stay on by force. And basically, these bone conducting headphones bypass the ear canal and the drum and directly excite the middle ear. You can see in the diagram up here that we're not actually exciting the eardrum, but we're using bone conduction to go directly to the middle ear. And that's both good and bad. The biggest difficulty with this style of headphone is that it's very hard to calibrate. There really is just not enough research about what the response should be, how to measure the response. There's not really any good artificial mastoids. There are some that were designed for hearing aids, but not really for bone conducting headphones. So it's kind of hard to know what the response really is equivalent to air conduction headphones. And typically, because the high frequencies get absorbed by the skin, it's kind of hard to get a good high frequency response out of these. But nevertheless, they've gotten a lot better. All right, so just like there are many different types of headphones, there are many different types of ears. In fact, no two pinnas are alike, just like a fingerprint. And what's even more remarkable is your left and right pinna and ear in general are not symmetric. If you want to hear a funny story about the original B&K hats head and torso simulator, the pinnas were not identical or mirror imaged because they were actually created out of a mold of Pear Brule. And big surprise, his left and right pinnas were not mirror images of each other. So eventually they changed that, but that was kind of confusing when you would get different measurements on different ears. And then, you know, I joke here that some people introduce acoustic leaks and into their ears, and I wonder what that does for the low frequency response. So I don't suggest putting holes in your ears. All right, so just like there are many different types of ears and pinnas, there's many different types of acoustic ear simulators. And here's just a smattering of a few. And you can see different companies make different ones for different applications. And again, one size does not fit all. Maybe the head and torso simulator mimics the human the best, but it also has certain caveats or trade-offs, which I'll talk about. So the most common class of acoustic ear simulators are below. I'm going to talk about it from left to right with increasing complexity. We start out with a very simple 2cc coupler, which is a single volume, a simple volume. That's why I don't even show a diagram or a cutaway of it. It was really used and still is used mostly for hearing aid testing. You could use it for earbuds, but I wouldn't recommend it. Then it's been around for ages, the IEC 318 coupler, which is also known for telephone testing and basically had a 3-volume design. Hopefully you can see my cursor. So a little more complex, a little more to represent the acoustic load of a human ear, but not very realistic when it comes to sealing like a human ear. So when people were testing handsets, one of the problems was how to get a good seal, and they had this what they call knife edge ring around the top, and you really had to make sure it sat flat on the receiver in order to get a decent measurement. Then there's this 711 coupler, which has also been around for a very long time, which is, I would consider, still the de facto standard used in most measurements and most ear simulators, such as the hats I show on the right. The 711 coupler is very, well, I wouldn't say very complex. It's pretty complex. It's got a lot more volumes and a lot more parts So again, it does a better job of simulating the real acoustic load of a human ear. And that's important depending on which type of headphones. We'll talk about that in a second. And then we got the head and torso simulator. Probably the three popular ones are B&K Hats, Grass Kemar, and Head Acoustics Artemis. So basically the advantage there is they have pinnas. The old Hats and old Kemar had the 711 coupler after the pinna or inside the mannequin head. And nowadays you actually have high-res versions of these as well. And I'm not going to dive into that because that's a whole nother topic. But generally speaking, the 711 coupler was designed for telecommunications, and its usable frequency range was really designed to be 100 hertz to 8 kilohertz, maybe 10 kilohertz if you stretched it. So clearly 10 kilohertz and above is not super representative of a real human ear. But then again, above 10 kilohertz, the human ear is not that precise. So let's talk about acoustic impedance for a moment. And the reason this is important is because, again, it affects our headphones measurements and what we have to be careful of depending on what type of headphones we measure. So it's just like electrical impedance. If we want to drive a low impedance loudspeaker, like some of these loudspeaker drivers in a car may be as little as 2 ohms because they're trying to maximize the voltage coming out of the battery. You want a super low impedance amplifier, and the lower the impedance of the amplifier, the greater the ratio between the driver and the amplifier, the less effect the load of the driver will have on the amplifier. And this is also the case with headphones. So what I call a high acoustic impedance headphone, such as your typical closed back, like Sony or Bose headphones, or insert earphones that go in the ear canal for a blocked ear, their response will be greatly affected by the acoustic seal to the ear. So this is why it's really important to use an ear simulator that represents the real acoustic load of a typical human ear. On the other hand, if you're using typically most of the time they're more expensive, these low acoustic impedance headphones that have open back. In other words, they transmit sound almost equally out the back and towards the ear, so other people who are not wearing the headphones can actually hear them. Those are typically not greatly affected by the acoustic seal to the ear. So they're much easier to measure in some ways on like a head and torso simulator because they're less position sensitive typically, and the low frequencies seal is not so critical. It doesn't mean they're not difficult to make though. They certainly are. So how to measure headphones? Well, bear in mind that headphones are typically, at least dynamic headphones, are anywhere from 2 ohm DC resistance to 100 ohms. Some of the studio headphones have a quite high impedance. But generally speaking, you'll see headphones that are nowadays, I'd say between 8 and 32 ohms. And then the lower the impedance, typically the louder you can drive them, but then again, you got to worry about the headphone amplifier having a low enough impedance. So quite often on the production line, impedance is not measured. And the reason for this, I think, is just mostly practical. If you got 2 earphones and 2 microphones to measure the acoustic response, you're going to need 2 impedance or reference resistors and 2 more input channels to measure the left and right impedance. And it gets a little tricky, especially if you have a wired cable with a common ground. So generally people don't do this now. Of course, less and less wired headphones are coming out today, so that's even another reason why impedance is not typically measured. But it is really important if you're measuring the raw transducer and you're trying to design the best earphone transducer possible before you add the electronics. Typically, headphones need anywhere from 10 millivolts to 2 volts, depending on the design. They can get quite loud, and this is where you got to be really careful because the earphone is right next to your ear canal. The loss due to distance is minimal, so you can get some really high sound pressure levels at the ear and damage your ears if you're not careful. There are different audio interfaces that we can use to connect to the headphone, whether it's wired or not. But we can also, and I'm not going to go into a lot of detail about this today, we can also use something like a Bluetooth interface or a USB interface and still, of course, get signal into it through a digital signal, because now it's going through some D to A converter and over a wireless transmission. And if we want to measure the microphone in the headphone or headset, and a lot of times now the more expensive headphones even have a mic array or microphones for active noise canceling, we need some sort of artificial mouth or loudspeaker if we want to measure that. And if we really want to get a little more sophisticated, we want to test the noise cancellation on the headphones with various background noises. So there are some background noise systems such as Listen cells that follow the ETSI standard, and that allows you to do playback of binaural recordings to simulate real world conditions, such as being on a train, a subway, in a car, and so forth. So I'm not going to go into detail about Bluetooth or ANC today. That's going to be in part 2 in the future. So R&D, generally I recommend using a head and torso simulator with PINAs because it's the most realistic. And the other thing to keep in mind is that the more realistic the head and torso simulator is, the more tricky positioning or more important positioning becomes, especially if you're trying to compare measurements between 2 different headphones, or even measure the same headphone on 2 different days. If you don't line up the headphone correctly on the pinna or in the same location, you can get a drastically different response, especially at the low frequencies. So generally what we recommend is, and standards recommend this, is that you measure the headphones at least 5 times by repositioning, taking it completely off and putting it back on, and then calculating the average response. So more lifelike situation where you just take your headphones off, and as we all know, sometimes we move them around to get a better seal. So speaking of seal, let's just talk about the effects of leakage on the frequency response. So a poor ear seal results in low frequencies rolling off. I think that's pretty obvious because now the low frequencies are allowed to leak out and not just directly coupled to the ear. And as I mentioned before, it depends on the acoustic impedance of the headphones. A open headphone, open back headphone, won't be as sensitive to this as a closed back headphone. But with earbuds, it's pretty much unavoidable because they just kind of dangle inside your pinna, unless you want to hold your finger there and try to seal them, which I don't think you probably want to do. They're particularly problematic trying to get repeatable measurements and good low frequency response. So what I recommend is whenever we want to measure our headphones is that we mount the headphone on the ear simulator and try to play around a little bit with the seal. And if we use a signal generator playing pink noise and bring up like a real-time analyzer, we can see real time if we have a good seal or not. So I'm not going to demonstrate this live, but I think you'll get the point. I have 2 signal generators going, one for the left ear, playing pink noise, 20 to 20 kilohertz, one for the right ear. I'm looking at the overall frequency response, and you can see that the left ear actually has a bad seal. So in other words, whether it's in-ear or even over the ear, I probably want to try to adjust it so that the left ear looks more like the right ear. And it is kind of a relative measurement, and you just kind of have to sit there and play around until you get the best possible seal. You may also find, depending on the size of the headphones, like I mentioned, the intraconcha, the ones that sit on top of the pinna but not circumoral, the high frequency will depend on the positioning on the pinna as well. So I always recommend doing this first before you make the complete measurement and measure things like distortion. I also recommend using this to set your levels, because generally, if you're going to measure distortion in particular, you want to be very precise about what level you measured the distortion at, because distortion changes with level. So in this case, you know, it's 86, 88 dB SPL. I might want to turn up the level until I get to 90 dB. Generally, that's kind of a default I use for measuring distortion, but there's no standard on that, so it's up to you. But you should specify it, especially if you're going to do comparisons to competitive models or even within your own product line. So now QC is quite a bit different. And QC, obviously, we have more background noise. We're not looking for necessarily the most accurate, or realistic, I should say, the most realistic measurement to the human head or ears. What we're really looking for is repeatability. And if we're going to, you know, put a head and torso simulator inside a noisy factory floor, I guarantee you we're not going to get a lot of repeatability, and we're going to get a lot of background noise. So generally, you want to use a simple coupler. If it's in the ear, it might just be a 711, and you somehow seal it well to the opening. If it's a circumoral, typically I recommend a headphone test fixture with either a flat plate, or maybe it has a coupler as part of the plate, but you have these alignment fingers and kind of a target so that you can make sure you get a very repeatable measurement. And if necessary, you can put it inside an acoustic test box. But if you have a good seal, because the earphone is so close to the measurement microphone in the ear simulator, you generally get a pretty good signal to noise ratio. But if you want to measure rub and buzz, you might need to put it inside a well-sealed box as well. So what are the critical measurements to make? So certainly frequency response, probably the best overall indicator of whether the earphones are working properly. Unlike loudspeakers though, a flat curve is not ideal unless you're subtracting out the ear simulator response. I'll talk about that in a moment. There are typically 2 well-known responses for ear simulators: diffuse or free field corrected responses, and those are standardized. I'll show you those in a moment. Of course, we want to measure sensitivity, because first of all, we want to make sure that the left and right ear are pretty close in sensitivity. You know, a 1 dB difference between left and right ear will shift the image. We also care about the sound pressure level, so we want to know the sensitivity, and we also want to know You know, if it's a small smartphone with a small headphone amplifier, of course, it's only limited in how much power it can produce. So more sensitivity is generally better. But again, we're going to wireless devices, so we have even less power inside the headphone amp chip. Phase and polarity is important. If they're out of phase, it will sound very funny. There will not be a lot of bass. And we basically want the positive input signal to cause the loudspeaker to move out. A lot of debate whether people can hear absolute phase or not, or polarity. Generally speaking, most people cannot. I can say that. We also want to compare the response between the left and right earphone. Again, it's important because we want to have a good balance. Distortion is important. We don't want the earphones, even though they are very close to the ear. We're actually able to probably detect more distortion, if anything. Generally, again, we have a better signal to noise, so the background noise is not swamping out the distortion so much. Rub and buzz is still probably the most critical distortion measurement, because anyone will complain that that sounds bad. I have a whole nother presentation just on distortion, audibility, and distortion measurements. So I'm not going to go into much detail about that today. I'm going to focus more on frequency response. I talked a little bit about impedance and resonance. Again, if you're measuring the raw transducer, this is important to know. Typically, the resonant frequency is much higher on the earphone than it is on a traditional loudspeaker. And you really want to be able to control that, because it will break up. You get breakup modes in the headphones, which do become audible and typically fall closer to the most sensitive frequency range of human hearing. And then, as I mentioned before, headphones can play quite loud and damage your ears. And there is a standard I'll talk about as well for maximum sound pressure level. So this is where things get a little confusing, because if we're used to measuring loudspeakers, as I'm trying to show in position A with a free field microphone pointed at the loudspeaker, ideally we want a flat response if we're in an anechoic chamber. So we can't measure headphones this way. We got to mount them in some sort of ear simulator. Otherwise, won't measure any low frequencies, for one. So what we do there is now we substitute the free field microphone, typically with 2 ear simulators, or at least 1 ear simulator. And right away you can tell there's a lot of differences. The microphones in ear simulators aren't pointing at the loudspeaker. We have shoulders which cause reflections, which you can see at the very high frequencies. So if you look at response B on the graph, you'll start to see at the higher frequencies a bump due to shoulder reflections. And you also see the ear canal resonance at typically 2 to 4 kilohertz, which is just inherent in all human hearing. We have this, basically the human ear is like a microphone with a horn attached to it. There's also some head shadowing effects as well. So we're not going to get a flat response, even if the headphones are perfectly flat. So what do we do when we're measuring headphones? Well, we can leave the ear simulator response as part of the measurement, but ideally, we'd like to subtract it out. We'd like to make the response be independent of the ear simulator, especially if people are using different ear simulators or different head and torso simulators. We'd like to know what the headphone response is by itself. So what we do is we measure what's called the insertion gain, which is the green curve. So that has both the essentially the response of the ear simulator with the ear canal resonance, as well as the headphone response or earphone response at the eardrum, and we subtract one from the other. And if it's the perfect headphone, we'll get a flat insertion gain. So again, back to what we're used to. Unfortunately, most people publish headphone measurements with the actual acoustic coupler response built in. So you kind of have to memorize by heart what that ear simulator response is, and I think it gets very confusing. So let's talk about different types of correction curves for different types of ear simulators. So now I have a frequency response of different ear simulators. I got what's called a diffuse field correction. This is coming from B&K Hats, this particular one. And the way it's measured is literally they took a head and torso simulator and they put it in a reverberation chamber and measured the acoustic response at the drum reference position. So all the sound is coming from every angle, not too realistic unless you listen to music in a reverberation chamber, but somewhat realistic in the sense that when we listen to music like in a concert hall or even a live band, there's a lot of reflected sound coming at you. And if we want to, we can use this blue curve as a correction curve. We can also use what's called the free field correction curve, which is measured by just pointing the loudspeaker directly at the nose of the head and torso simulator and measuring the sound pressure level at the drum reference point. Sorry, I didn't mean to show that. And as a result, we get a more dramatic peak at the ear canal resonance because of it just being one angle. We also get a bump. I think this actually is a lot due to the shoulders at like 12K. So at low frequencies, it's not hugely different, but at high frequencies above, 4 or 5 kilohertz, it's definitely very different. And again, we don't listen to music or speech in an anechoic chamber, so it's also kind of a compromise. The next thing worth mentioning is it's become very popular, the Harmon target curve. They actually have two. One is for over the ear and one is for in ear. And they're a little different, but the primary difference is actually the low frequencies, which Sean Olive and Harmon haven't really come up with a great explanation for. I have my guesses, but I think I'll hold my guess until I can prove it out. But basically, you'll notice that low frequencies, there's this boost, and it's generally because we're used to listening to loudspeakers in a room, and typically the loudspeakers are in the corner of a room, so they inherently get this low frequency boost from room, you could say room reflections, or just the corner loading of the loudspeaker. So as a result, most people expect that same bass boost in their headphones. And that explains why a lot of times headphones don't sound like they have as much bass. I mean, there is also just the physical vibration of the bass, which you don't get as much viscerally with headphones, but even so, there's a lot of debate about that as well. And you can create shakers and things like that. But you notice that the Harmon target curve, to a certain degree, has a similar shape to the diffuse field correction curve. And then Harmon decided above 10 kilohertz just to roll off the frequency response or the target, partially because it's just very unrepeatable. As I mentioned, the 711 traditional couplers don't really accurately reproduce human hearing above 10 kilohertz. And it just decided that it would be easier to make a standard curve. And the principle here is an interesting one. So instead of working backwards from the ear simulator. They're kind of working backwards from subjective listening tests. So they go around and they have hundreds of people at different ages, different sexes, different origins, listening to music, and they simulate different headphones, and they try to basically come up with the ideal headphone frequency response based on listener preference. So one thing you got to be careful about is that it is an average, and even though you can probably come up with a reasonable average that will make most people happy, it definitely won't make everyone happy. Some people prefer more treble, some people prefer more bass. That's one of the things they found with the younger listeners, that they preferred more bass. But in any case, what they did was they came up with this target curve by just simply synthesizing that headphone that everyone said they preferred, and then measuring it on a 7-11 coupler. And another thing that you got to be a little careful of is they modified the pinna on their 7-11 coupler, so it isn't even a standard pinna. So just be careful and don't be too surprised if the Harmon target curve isn't always the best curve for your headphones. It really is, what I like to think of it is, it's a good target to start off with. But then I think you really should fine tune it to meet what you subjectively think is good, or what your panel of golden ears think is good. So down below we have what I like to call the corrected curves. So we take the left earphone response with the ear simulator. This is measured on a head and torso simulator. And then we apply the correction curves from above. So we just basically divide them out. And you can see that for this particular headphone, which I believe is in-ear Etymotic 4S from a long time ago, which is really quite a good earphone. When you do the diffuse field correction, you get a fairly flat response, flat frequency response, or insertion gain, and that was their intention. So at the high frequencies, it rolls off, and above 10 kilohertz, the ear is not super sensitive anyway, so it's probably not so bad. But you can also see the free field corrected curve will have this bump, which is due to this on-axis reflection off the shoulder. So I wouldn't worry too much about that. But this is kind of a de facto standard, but now a lot of people are using the Harmon target curve, and I'll show you a way to compare to the Harmon target curve as well. So the way Harmon does this is they measure the headphones. For example, the AKG 701s, which is a Harmon product, which is open back. I actually think it's a great headphone. It's been around for ages, and it was one of the first headphones designed on a Roland-Care head and torso simulator back in the 80s. I know the designer. He used to work at B&K. And interestingly enough, it does pretty well. Like I said, it was designed to meet the diffuse field corrected curve. So it overlays pretty well. So you see the green curve is the Harmon target curve, and then the blue curve is the actual response. Of course, there's some high frequency cancellation going on. Maybe there's cone breakup, maybe there's standing waves inside the ear and the coupler. And ideally, if the headphone response or earphone response matches the Harmon target curve, you will get what they call a flat error curve at 0 dB. So the red line ideally should be flat at 0. And since it's not, what they do is they calculate a predicted preference based on how far it deviates from 0 dB. And then they also take into account some of the slope changes in the response. It's all part of an Excel spreadsheet. And they, again, only focus up to 10 kilohertz because above 10 kilohertz, it's all over the place. And the ear simulators aren't very repeatable there. They also only go down to 50 hertz. And I think that's because the seal is so crucial as well that they're trying to make it a little easier not to have the perfect seal. They average the left and right earphone response. I think they do that to keep it simple. I think it would probably be better to do them separately. And they don't take phase into account, which is another controversial thing. I actually think phase does matter. And if you ever attend my high-res headphone presentation, I will explain why phase matters at high frequencies, because it actually impacts the phase at the lower frequencies. Not that people can hear about 20 kilohertz, but we actually, there's been subjective listening tests that show with headphones and the right kind of music, actually around 2 to 4 kilohertz phase does matter considerably. Anyhow, moving along. So if we want to have good imaging, we want to have good left-right channel balance. And again, ideally, we want a flat curve at 0 dB, and we want a flat phase curve, ideally at 0 degrees. So this particular headphone, and this is where in-ear headphones, you got to be really careful with how far you insert the left earphone relative to the right earphone. I discovered kind of a neat way to balance that by using what we call the auto delay algorithm that measures the distance through the speed of sound, so that if your one earphone's in tighter than the other right earphone, you'll get a sensitivity difference. You also get quite likely a phase difference at the high frequencies. So there is a technique where you can try to insert them at the same depth using acoustic delay. So again, if we want to do virtual reality, we want to reproduce sound in space, we want to make sure that the left-right balance is very good. And we can do this very easily in sound check using post-processing. So getting towards the end now, bear with me. So Max SPL was the safety standard. It was introduced, I believe, I forget the exact date. I believe it was in the 90s. It's a British standard. I always like to joke that it's a BS standard. But the reality is that many people do play music too loud on their headphones. By the way, you can tell it's an old standard because the head and torso simulator has a cassette player or like a Sony Walkman hooked up to it. So maybe it's from the 80s. I can't remember now. So basically, you notice it has a free field compensation filter that is a free field correction curve. So I don't, probably they should have used maybe the diffuse field correction curve, but that's what it is. And what they do is they use shape pink noise that's supposed to be more like music. I think pink noise would be good enough personally. They measure in third octave bands real time because that's a rough approximation of human hearing frequency selectivity, but that's certainly an oversimplification. And again, the importance of repeating the measurement 5 times by removing and replacing the headphones. And then they look for a weighted 30-second response. I think you can measure for 30 seconds or 2 minutes, I forget. And from that, they calculate the equivalent noise exposure. So what you need to do is know if it's in the US, the ANSI standard or OSHA recommends no more than 90 dB SPL, A-weighted, up to 8 hours. Otherwise, you're damaging your ears. And in Europe, it's IEC standard, I believe, and it's 86 dB. They're a little different, but generally speaking, listening to music for a long time at a loud level is going to damage your ears. And that's why live concerts are so incredibly dangerous to the ears, because it's not uncommon for them to be like 110 dB SPL. And all it takes is a few minutes of that to damage your ear. So this standard is enforced mostly in Europe. I don't think it's really enforced anywhere else, but it's certainly something that we have a sequence that can test to this, and I recommend that. All right, so now it's time for a little demo. And what I'm going to do is briefly pause screen sharing so I can show you sound check screen. All right, so headphone demos are a little boring because you can't hear anything. So I'm just going to cheat a little and use recalled data. And this is a sequence I made back in the early 2000s. Because I didn't want to carry a head and torso simulator or even an ear simulator for demos. So I measured, in this particular case, it was etymotic in-ear headphones, and I saved the raw recorded time waveform. So instead of saying I want to measure live, I'm just going to recall the data. And of course, it doesn't have to be that waveform. It could be other headphone waveforms. And you can see, very similar to what I showed you before, left and right earphone response, and the equivalent sensitivity over 100 to, I believe I went up to 10 kilohertz. So an average of 106.5 on the left earphone and 107.6. And you can see that slight difference in the left-right tracking. And if you want to see the phase, you can just go turn phase on and auto scale. So now you have what I showed before. But let's just focus for a moment on the diffuse field corrected and the free field corrected. Now I'm only showing it for the left just because I didn't want too many curves on my graph at one time. But again, this headphone was designed with diffuse field correction in mind and is actually pretty flat. On the bottom screen, I have THD for left and right. The driver inside this headphone is a balanced armature and actually has pretty low distortion. And you can see at high frequencies, it's pretty smooth. At low frequencies, it's going up considerably, but that's really a result of the low frequency roll-off. And what I like to talk about in my distortion seminar is normalized distortion, where we actually take into account the linear response and how it filters the distortion response. And if we did that, you would see it would be well below 5%. So that's just kind of the nature of the high pass filter of the headphone. So pretty good headphone. And certainly if you want to put limits and calculate pass-fail results on a variety of things, you're more than able to do that. The other demo I'd like to show you is the Harmon target curve. And I'll just bring that up for a moment. I'll discard this. And here again, you know, measuring a pair of headphones and not hearing it's pretty boring. So I'm just going to recall some measurements I made. This, so the first thing it does is it loads the Harmon target curve. Then it asks me for, these are time waveforms typically, or they can be curves. And I'm going to go for AirPods. I'm actually using AirPods Pro tonight for whatever it's worth. because they stay in my ear, unlike the regular AirPods. And you can see the left and right track pretty well, and actually fall on top of the Harmon target curve pretty well. And then you see the air curve below. Now what you didn't see was a Excel spreadsheet pop up. And what I'm going to do for a moment is, I hope I can do this, is show you the Excel spreadsheet. And again, I think I'm going to have to switch screens. And share the spreadsheet. So now you see the raw data that Soundcheck exported to Excel. And if I scroll left, you now see the preference rating based on the measurement. Now this is an interesting example of how the low frequency response dramatically impacted the predicted preference, because it's actually pretty flat above 100 Hertz. The error curve is pretty decent agreement up to 10 kilohertz. But because the earbuds aren't giving you a good seal, you get a big difference between the Harmon target curve, which goes up at low frequencies, and the AirPods, which roll off. So that's it. I just want to thank everyone for joining.